Okay. Good morning, everyone. A warm welcome to all of you at the Shiv Nadar Institution of Eminence. I'm Vinny Mathur, and I work at the Office of the Vice Chancellor. I will be your MC for the event this morning. I would now like to call upon stage our respected Vice Chancellor, Dr. Ananya Mukherjee, for her welcome address.
Good morning. A very, very warm welcome to all our distinguished guests, Professor Serge Haroche, Dr. Nitin Seth, Director of the Indo-French Center for the Promotion of Advanced Research, Cefipra, Attaché Rabioso, our deans, faculty, students, and visitors who have joined us today. This event marks a very special day in the life of the Shiv Nadar Institution of Eminence. Research, as we like to say, is the backbone of our institution. Our aspiration is to produce research that changes the world, but also to foster an excitement about research that is powerful and enduring. Accordingly, research is built into our curriculum in an integral way. We are privileged to have a research infrastructure that is rare in the global south, and we are adding to that infrastructure every day to further expand an exceptional research environment. From experimental and theoretical condensed matter physics, high energy physics, to advanced materials, green chemistry, disaster management, cybersecurity, Shiv Nadar researchers are making their mark in many areas. As an institution of eminence designated by the Government of India, we wish to be fully engaged in the research priorities of the country, such as quantum technologies. The National Mission on Quantum Technologies and Applications provides a great platform to advance quantum research as well as to advance India's position as a leader in this area. Of course, we wish to be part of this bold ambition, but we are only 12 years old. And for that, we need exactly what we have here today: a Nobel Laureate, leading scientists in the area, and an audience of curious teachers and learners. This could be the beginning of a new journey, a new dream. In the words of our founder, Shiv Nadar, a dream has no size, no dimensions, just dream big. So with this, I welcome you to today's proceedings. Thank you.
Thank you, Dr. Mukherjee. I now like to call upon Dr. Nitin Seth, Director of the Indo-French Center for the Promotion of Advanced Research, to say a few words. Thank you.
Thank you very much, Professor Ananya, for hosting us in such a beautiful auditorium. And well, I would personally say it's not a too young university. I would say that it has been conceived with a brainchild of research. So any university which is backed up with the foundation of research and a strong orientation towards teaching passions of research will definitely know when to stop on that. So I'm sure that this will be very good university. Well, I am also a professor sitting on this side now, holding a responsibility of Indo-French Center for Promotion of Advanced Research. So first, I would like to thank Dr. Ananya for hosting us here, Professor Galande, Professor Shantanu for such a nice welcome, such a nice gesture. Well, Cefipra is a body which has been set up by both the governments, that is on Indian side, it is Department of Science and Technology, on a French side, it is Ministry of Europe and External Affairs. So the idea and mandate of this particular body is to promote the research on both sides, bilateral research, My friend Dr. Didier is there. He will talk more on the research part and the other aspects which we deal. As far as the mandate of Cefipra is concerned, we generally invite the people from both the countries to go for a knowledge exchange platform. So Cefipra is basically a body, you can say, facilitating the exchange of knowledge on both countries. We generally provide different opportunities for students as well, researchers as well. I am not here to talk on Cefipra program because today is not the day for Cefipra program, so I'll not take much time on that, but please do visit Cefipra website and see what are the programs which are offered for both faculties. As a faculty, I would only say that we have multiple programs to apply for the Indo-French opportunities for research. We have a program for women researchers as well for an exchange programs. We have project calls wherein we provide funding supports for Indo-French joint research. We have collaborations on many aspects with the industries of French. We have dedicated calls for research on water supplements. We have a network call on data sciences. We have a network calls for One Health. So probably more details are available on Cefipra website. But last but not the least, I once again thank Professor Ananya for giving us a chance to speak. Thank you. Thank you.
Thank you, Dr. Seth. I would now like to invite on stage Dr. Didier Aboinsin, Attaché for Scientific Cooperation, Embassy of France and India. So may we kindly have you on stage, please, to address the audience.
Hello, everybody. Thank you so much to Shiv and Nadar University for your warm welcome. We are very pleased to be there today. I want to thank Hananya Mukherjee for your warm welcome and to make it possible today. I want also to thank all people involved in this event, Dr. Sanjeev and Dr. Sunzansa. As attaché for scientific cooperation, my work is to make sure that France and India have a very nice and very fruitful cooperation in science. And we are very pleased to have Dr. Serge Haroche, Professor Serge Haroche today between us to exchange of what could be done around, around physics and quantum. I just want you to give you two numbers and to highlight two opportunities. The two numbers are 42%. 42% is a percentage of PhD students in France that who come from abroad. So it means that France is very open to the world, and we really welcome you to have your PhD in France for fruitful cooperation. The second key number is 2000. 2000 is a number of masters totally taught in English right now in France, and I also welcome you to have a look on which master you can follow in France in English in the future. I also want to highlight two opportunities. Professor Nitin Seth has highlighted the opportunities offered by Cefipra. Cefipra is act as a funding agency. We have 4 million euros per year for funding research between India and France, and I highly suggest you to have a look on the website to find all the projects or the program we offer for you. The Embassy of France in India also support student mobility, and we devote 1.7 million euros to welcome Indian students in France. So I highly suggest you to have a look on our website, and we now support student mobility from bachelor's up to PhD student, and we have also some program for postdoctoral, and we have also now some program for mobility of staff and academics. So I highly suggest you to have a look on the Cefipra website or the Embassy of France in India website. Once again, thank you so much, and hope to see you soon in France or elsewhere. Thank you so much.
Thank you, sir. May I now request Professor Sanjeev Galande, Dean, School of Natural Sciences, to introduce our speaker for the day and esteemed guest of honor, Nobel Laureate Professor Serge Haroche.
I'm really honored to introduce Professor Serge Haroche to all of you here today. When it comes to the minute components of the universe, one's usual understanding of how the world works ceases to apply. We have entered a realm of quantum physics. For a long time, many quantum phenomena could only be examined theoretically. In the 1980s, Professor Haroche designed ingenious experiments to study quantum phenomena when matter and light interact. Professor Haroche has been able to capture photons using another kind of a trap, two mirrors which can bounce in between. This device allowed Professor Haroche to study the photons by passing atoms through the trap. Professor Haroche works primarily in the fields of atomic physics and quantum optics. He's principally known for showing quantum decoherence by experimental observation while working with colleagues at the École Normale Supérieure in Paris in 1996. For this work, Professor Serge Haroche was awarded Nobel Prize in Physics in 2012, jointly with David Wineland for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. A study of the fundamental particle of light, the photon. He has pioneered a research field called cavity quantum electrodynamics, which plays an important role in the development of quantum information science. I must add here that Professor Haroche's PhD supervisor, the French physicist Claude Cohen-Tannochi, was also a recipient of the Nobel Prize in 1997. After PhD from such a great school, Professor Haroche worked at CNRS, Stanford, and Paris University. So he has been traveling around the world learning and studying physics. He also taught at other universities such as École Polytechnique, MIT, Harvard University, and many others, including Yale and many other universities. He was head of the physics department at the École Normale Supérieure from 1994 to year 2000. Professor Haroche currently is an emeritus professor at Collège de France in Paris and a member of the French Academy of Sciences. He has received numerous awards and fellowships, commander of the French Legion of Honor, and a fellow of the European and the American Physical Societies, to name a few. In 2020, Haroche was appointed by the European Commissioner for Innovation, Research, Culture, Education to serve as an independent research committee for the next president of the European Research Council, ERC. Professor Haroche is a man who followed his dream. With his elementary knowledge of calculus as a child, the boy Serge was able to compute and escape velocity of rockets, the periods of satellites on their orbits, and the gravitational field at the surface of all the planets. The astonishing fact that nature obeys mathematical laws and the mysterious beauty of the quantum world inspired the child in Professor Haroche to become a quantum physicist. While Professor Haroche puts much weight on time, trust, and money, he believes that the most important factor of the success of his research has been the quality of the people he has had to luck to work with. He finds teaching very rewarding, with an indiscriminate interest in literature, history, mathematics, and physical sciences. Professor Haroche has maintained in his life an enriching balance between science, arts, and humanities. We are indeed fortunate to have him with us today, and I warmly invite him to the dais to deliver his public lecture. Professor Haroche.
So, good morning. I am very pleased and honored to be here and to have the opportunity to talk and to address such a large and interesting audience. I would like to thank Madam Vice Chancellor of this university, and also the Cefipra and the French Embassy for organizing this visit. In fact, I have not prepared a talk for you today. I was told that we will be talking about quantum technologies, and I would like to start by saying a few words about this field and about science in general. I am impressed by the fact that this young university is devoted to research, as I've been told, and interdisciplinary research in biology, physics, engineering, and I think it's very important for research to be based on basic science. And we will be talking about quantum technologies, and I would like to say a few words about the way this field of quantum technology was born. We talked about quantum, and in fact, quantum physics has been around us for more than a century now. And we are in 2023, and just 1 century ago, in 1923, Einstein received a letter from an Indian physicist, Bose, who he was a young scientist. He had tried to publish a paper on a new statistics to understand how photons behaved and how thermal photons could be analyzed. And his letter was not accepted for publication. So he sent the letter to Einstein, and Einstein found it very interesting. He found that the way Bose was calculating the statistics of photons was different from what Boltzmann had done 20 or 30 years earlier. And he helped Bose to publish in a German paper his article, and Einstein started from then on and found that if you use these statistics for atoms, you would find a new phase of matter, which later was called Bose-Einstein statistics. It took 75 years from Bose and Einstein paper to the observation of Bose-Einstein statistics with cold atom back in the 1990s. And this gave rise to a new field of physics using ultra-cold atoms to achieve interesting results. So it tells you something about the connection between basic science and applied science. Basic science is just born out of curiosity. And then, after many years, you find ways to apply this for devices which might be useful. For example, using ultra-cold atoms, now there is a field called atomic interferometry, which was born and which makes it possible to measure things, for example, to measure the gravitational fields, to build accelerometers and gyrometers, which might have very interesting application for navigation, for instance. This was born for basic science. Another example is also related to Einstein. A few years earlier, in 1916, Einstein had the idea of stimulated emission, the fact that when atoms interact with light, there is a phenomenon which was not known before, which leads to the amplification of light. If photons fall on atoms, the atoms have a tendency to emit photons in the same mode, with the same frequency, the same direction, the same polarization as the impinging photons. And it took again something like 40 or 50 years before stimulated emission was used to build lasers. And the lasers started at the end of the 1950s and 1960s. And now we know that the lasers are devices which are used in a very, very large number of applications for basic science, but also for technology. And this was something this is a trend which took a very long time to mature, and now it's a huge industry. Lasers, it's a market, there's a market of several tens of billions of dollars a year in laser industries, in all range of activities, going from communication, all of the optical fibers which convey the signal of the internet are based on the laser technology, and there are many, many more uses of lasers, in applied science, but also in basic science. For example, the discovery of gravitational waves has been made in gravitational antennas in which laser light is propagating between mirrors separated by kilometers from each other, and the laser is of course essential for that. Lasers are also used to build atomic clocks now, optical clocks, which count the period of light and which have a fantastic precision, and many applications can be envisioned for that. So my main wish is to really emphasize the fact that basic science is essential for all these applications. And this is the case for the quantum technologies that we will be talking about in a panel discussion today. We are now talking about a second quantum revolution, quote unquote. I don't like too much this definition for reasons that I will explain, but this means that there was a first quantum revolution. In fact, all the devices that we are using in our everyday life come from that. If you talk about the GPS, for instance, GPS is based on atomic clock, microwave clocks, which are sent in satellite around the Earth, and of course, this is a quantum technology. The MRI, magnetic resonance imaging, is based also on quantum knowledge, the fact that you have spins, magnetic moments on atoms in our body, and that you can detect this by nuclear magnetic resonance techniques, which is also a quantum technology. The lasers that I have already quoted, and even the computers that we use today in our everyday life are based on the properties of transistors, in which again you need quantum technology to understand exactly the way they behave. So the first, what we call now the first quantum revolution, was essential to build all the devices that we use in every day without noticing that it comes from the quantum. At that time, when the founding fathers of quantum physics, including Einstein, were discussing, they did not say, we are doing a quantum revolution. They just did it, and the application came much later. I think today we have a tendency to show off a little bit and to talk about the second quantum revolution. I think we just have to do it and not to advertise it too much and not to make promises, because we don't know exactly what the future will be about. We know that we need to do basic science, that we have to keep investigating because we are motivated by curiosity, but the application will certainly surprise us. Everybody is talking about the quantum computer, and we might talk about that later in the panel discussion, but we are very far off having a quantum computer according to what we dream about, but certainly what will happen will be applications which will be useful, and maybe some of them will be more surprising than the quantum computer, when we have understood deeply what the quantum complexity is about, what quantum entanglement can bring to us. We'll certainly have some applications that we don't think about today. So I think we should keep open to all possible surprises, to all applications which might come from this kind of research, and not try to promise too much and to give too precise application, because there will be certainly surprises, and this is what what science is about. You cannot just predict what we will observe, what will be the future, because if we could do it, then it will no longer be research. If you know what you are expecting, then you are limited in the way you are doing your work at in the lab. In my case, I can give you a little bit, I can remind you of what I have been doing myself. It has been already described in the introduction. When I started doing my own research back in the 1970s, I did not know where it would lead me to. It was a time I was lucky to have started at the time when the laser was just invented and the lasers were improving, becoming more powerful, more precise in the frequency range in which they were able to excite atoms. And I just started doing this kind of research without any specific goal in mind. I started working with what one calls Rydberg atoms, very excited atoms in which you take one electron and you promote it to a very large orbit. So it's an atom which has very exotic properties, quite different from ordinary atoms. In an ordinary atom, in the ground state, the electrons are very close from the nucleus. The size of the atom is about 1 angstrom or a few angstrom. In Rydberg atoms, the size goes to half a fraction of a micrometer, 1,000 times larger than ordinary atoms. And these atoms are just very sensitive to all perturbation because the electron is very weakly bound. So I had the intuition that with these atoms, one could do things which are impossible with ground state atoms, that these atoms will be very sensitive probe of their environment, and in particular, very sensitive probe to radiation. So I started working with my team about ways to excite these atoms, to prepare them, and then to have them interact with microwave photons in cavities. So we started also to improve the quality of cavities in order to be able to see phenomena involving less and less photons, smaller and smaller field interacting with smaller and smaller number of atoms. The ultimate goal was to look at the interaction of a single atom with a single photon, because this is the most basic phenomenon you can think of in light-matter interaction. You take the simplest form of matter, one atom, and the simplest element of light, one photon, you put them together and you look at the way the atom exchange energy with the photon field. So this was our dream, and it took us many, many years to achieve it, improving the quality of the atoms by exciting them with light which was purer and purer with better and better lasers, and also improving the quality of our cavity so that the mirrors could reflect light with less and less losses. And eventually we got to a cavity in which the photon could bounce between the mirror billions of times, propagating on a folded trajectory, which if you extend it would make about 40,000 kilometers. In fact, our photons could stay in the cavity for 1/10 of a second, during which we could look at the interaction with the atom in a more and more precise way. What we could achieve in the end is something which is quite different from the way we look at light usually. If you think about it, if you look at the phenomenon of seeing, what happens that the photons come into your eye, and on your retina the photons are destroyed. They are transformed into a electric current or chemical signal which goes to your brain, but the photon is dead when this happens. And what we were dreaming of is to be able to observe the photon without destroying it. And for that, we discovered a way to do it by having atoms interact in a non-resonant way with light. The atoms could not absorb the photon, but there was a small perturbation on the energy levels of the atoms, which we could detect. And so we could detect the same photon several times. We could have atoms coming one by one through our cavity, and all the atoms saw the same photon. This allowed us to store some information in the cavity, one atom storing the information, and then the other atoms coming after that and reading out this information. And we did that only because it was a challenge. We could do it, and we wanted to observe and to find out what was the consequences of that. At the same time, in the United States, Dave Wineland, who shared the Nobel Prize with me, was doing similar experiments, but in a different context. What he was doing is trapping atoms and looking at using light to excite these atoms and to observe how they behave. So it was a kind of complementary experiment. In our case, we were trapping photons and using atoms to observe the photons, and he was doing the opposite. He was trapping atoms and using light to observe what was going on. And these two sets of experiments use the same kind of theory, light-matter interaction, quantum properties of light-matter interaction, and they were looking at from different sides to the same kind of effects. And we were, in fact, motivated by kind of competition between us, and some of his experiments were triggering our interest and led us to do similar experiments with our system, and the opposite was also true. And we were not thinking at all about quantum information. In fact, I did not know what it was, and I think it was the same with Dave. And then in the middle of the 1980s, some theorists, mathematicians and theorists, started to wonder whether the strange laws of quantum physics, the notion of state superposition, of entanglement, could be used to process information in ways which are different from the classical way it is done. And so these people start to think about quantum algorithms. This was triggered in particular by the experiment of Alain Aspect in Paris, beginning of the 1980s. Alain Aspect was recognized with Anton Zeilinger and John Clauser for having observed this entanglement by the Nobel Prize of this year, 2022. But this, the properties of entanglement were in fact at the foundation of quantum physics. Schrödinger had introduced the concept, but it had never been observed on individual particles. Aspect did that. It was just considered as some basic science, and then theorists and mathematicians have started to wonder whether this could be used for application. And the experiment that we did in Paris and that Dave Whelan did showed that it was indeed possible to manipulate single quantum systems. So sometime in the 1990s, at a meeting in Boulder, Colorado, one of specialists of the theory of quantum algorithm and quantum communication, Arthur Eckert, came and he explained to us, he told us, in fact, what you are doing in your experiment, you are building quantum gates. When an atom interacts with a photon, you can consider the photon as a control quantum bit and the atom as a at the target bit. And in Dave Whelan experiment, when you have two atoms in a trap, one atom can be considered as a control bit and the other the target bit. So what you are in fact doing are elementary experiments showing that it is possible to use quantum logic to do this kind of thing. And so we started working in this direction, trying to demonstrate that on toy system, on very simple system, it was possible to build quantum gates. And from then on, the field has, of course, taken a much bigger importance. A lot of labs in the world are working on that. But to build a quantum computer, there are formidable challenges which are still ahead of us. The big problem is decoherence, which has been mentioned in the kind of introduction I had to this talk. Decoherence destroys the quantum superposition very fast, and it explains why our macroscopic world is classical. In fact, as soon as quantum systems are exposed to the environment, the entanglement between the systems, the part of the systems that you can control is diluted, is an entanglement with the external world. And the entanglement with the external world destroys the entanglement which would be useful for quantum computing. So the big challenge is to be able to control this decoherence, to correct for decoherence when it occurs. And this is a very difficult challenge because it is somewhat paradoxical. We want at the same time the system to be isolated, and you need, of course, to get information because you are in the outside world, you are not part of the system. And so it's very difficult at the same time to have a system which evolves in a controlled way and to extract useful information from it. And nobody knows now what will be the best system for that, and also what would be the best way to do it. In fact, there are some ideas to control decoherence. It's called quantum error correction, but it's very far from achieving the goal, which is to have a very large system in which you would control everything to get a quantum computer working. But in the meantime, we are making a lot of progresses. There are a lot of other fields in which these methods are being used to, and we all know that there are at least 3 or 4 different directions which to achieve to obtain new quantum technologies. One is the quantum computer, as I have just talked about, which is the most difficult task. This is what we call a digital quantum computer, a quantum computer in which you would have quantum gates connecting atoms or single quantum system to each other in a very well-defined way, step by step. This is the analogous of a classical computer, but using quantum bits instead of classical bits. So this is a very difficult goal. But you have also what we call analog quantum computers, system in which you put single quantum systems, for example, atoms, at well-defined position, and you can tailor the interaction between them, and you let the system evolve without trying to correct the errors. And this is, so it's like a system in which you have a quantum interaction between the system evolving with all the noise which is coming with that, and this is called quantum simulation. It tries to simulate situations that you have in real systems, and this is already working, and it might have interesting applications, and we might discuss about that. We have quantum communication using the properties of entanglement to send photons very far apart from each other and use the quantum entanglement to communicate without possibilities, without any ability of spying upon these communications. It's called quantum cryptography. And you have quantum metrology, which is the field in which you use the sensitivity of this quantum system to build devices which are much more sensitive than you can do with classical system. One example are the fantastic atomic clocks, which now have a precision, unbelievable precision. You have clocks which measure time with a precision such that if you had 2 clocks which had started at the beginning of the universe, they would not depart from each other by more than 1/10 or a 20th of a second. So this kind of precision opens a lot of possibilities to measure the way gravitational fields vary, and many applications to basic science and to applied science might be envisioned. You can also use quantum probes to measure very small electric and magnetic fields, which might have interesting applications in biology, for instance, to measure the fields very close to molecular membranes. And so there are a lot of possibilities which are opened by these technologies, and a lot of research which remains to be done. So I think it's a field which is thriving, which would have interesting applications. I have only one piece of caution, one advice to give is not to oversell it too much, not to pretend that we are doing things that we are not sure that we will be able to do, because overselling may have negative results. There is a lot of money going into this field now. The money, I think, is well used, provided everybody understands that the quantum computer is a kind of metaphor for a lot of other things which are interesting. Now, to say a few words about France, there is a lot of research in France going on in this field. In basic science, France is very strong with cold atoms. It was mentioned that Claude Cohen-Tannoudji got a Nobel Prize for inventing ways to cool atoms and to trap them, and this has been a very active field of research in France, in my lab, Laboratoire Castor-Brossel, but also in other labs. There are not only academic research in this field, but also research by startups. There are startup companies. One of them is called Pascal, which is a company which prepares arrays of cold atoms in optical lattices and make very interesting and very promising quantum simulators using Rydberg atoms in optical lattices. There are also startup companies working in photonics, And there are startup companies working with superconducting qubits, artificial atoms made of superconducting junctions. And this is another area in which quantum information is going. There is also good research in quantum metrology, atomic interferometers for measuring small rotation, gyrometers and accelerometers. And this is also something which is supported in France. The government has started a big initiative which is funded by more than 1 billion euros, I think, in order to develop these technologies. And this is part of also of a big effort at the European level. There is a European flagship in quantum information, which just indicates that the same kind of programs are developed in other countries in Europe, in Germany, in England, even if England is no longer part of Europe. So it's a very big effort. I think it has to remain something which is done at the international level with a lot of cooperation between countries. And we need to develop this cooperation because we need basic knowledge, and basic knowledge can only be acquired by competition, by emulation between countries. One danger that I have seen in this field is that the governments and the politicians have the feeling that there will be, we are on the verge of discoveries which will give a kind of strategic advantage for some countries over others. And this has a very negative effect, the fact that it becomes more difficult for students and postdocs to travel from one country to the other because there are some visa restrictions. I know, for instance, that some Chinese students have been denied visa to come in France to do this kind of studies. At the European level, I know that the ERC, the European Research Council, has been restricted. There were some threats that researchers from Israel, for instance, would be denied to grants because they are not part of the Europe, and that the competition should protect the research in Europe from interferences from outside. Even the UK, which left Europe because of the Brexit, has problems to be involved in the research programs. I think this is very bad. I think this comes from a kind of paranoia for which scientists are partly responsible, because if you oversell, if you explain that the quantum computer will solve all the problems that we have today, clearly you create a situation which is not good for basic science. So I think we might discuss that too. We might try to find a good way to use the money which is coming in this field with an understanding between scientists and politicians about what we are doing and about what are the real goals of this kind of research. And I think part of the problem comes from the fact that in general, the people who are responsible at the highest level in politics are not scientists. And we have to be able to discuss with them and to make them understand what we are doing, the value of science, and how science can help solve the problem of society in a realistic way. It's sometimes more difficult that to open this dialogue in a constructive way between scientists and politicians, and we may also discuss that point. But here we are mostly between scientists, and I'm sure that we will have a fruitful discussion about these topics. So I think I will stop at this point, and thank you for your attention.
Thank you, Professor Haroche. Thank you, Professor Haroche. We'll request you to kindly stay on stage for the panel discussion. It was a very stimulating lecture. May I now request Dr. Galande to kindly come on stage and introduce the panelists? Thank you.
So while the panelists are settling in on the chair, I just thought I'll summarize two very important points that Professor Haroche brought out in today's talk. First and foremost, that politics and science should be kept away, and it's really very important that our politicians realize this. And secondly, he emphasized the importance of basic science. Many of us don't even think that quantum technology is anyway going to touch our daily lives, but he has given some very nice examples, starting from GPS to smartwatches to whatnot. And of course, all these products have come through a large amount of research that basic scientists have put in over decades of hard work. And he also alluded to what is going to come in future, so which is going to be maybe quantum computers. So, and of course, he cautioned that one should not extrapolate too much, that these technologies might eventually do something which they may not even promise. So these are some very nice points that he brought forward. And I'm now very happy to invite the panelists. The first, Professor Urvashi Sinha. She is a faculty member in the Light and Atomic Matter Physics Group, very nicely acronymed LAMP, at the Raman Research Institute, Bangalore. She is also an affiliate member at the Institute of Quantum Computing, Waterloo, Canada, as well as the Center for Quantum Information and Quantum Computing at the University of Toronto. She has been a Homi Bhabha Fellow in the year 2017 and a Simons Emmy Noether Fellow at the Perimeter Institute, Canada. Professor Sinha. Her research interests are in the field of experimental quantum information and quantum computing, as well as quantum cryptography.
Seating arrangement.
Yeah, second. Yes. I would now like to invite Professor Umakant Rapol from the Indian Institute of Science, Education and Research, Pune. Professor Rapol is a faculty member at the Physics Department at IISER Pune, and he heads the Atomic Physics and Quantum Optics Laboratory at IISER Pune. He is also the project director of iHub, a quantum technology initiative at IISER Pune, and he has also been a visiting researcher at ENS Paris. And as he's shaking hands with Professor Haroche, I must add here that they probably shared the same floor space at ENS. And Professor Rapol has actually worked with Professor Haroche's PhD supervisor, Dr. Claude Kanuji, who is actually also another Nobel laureate himself. Professor Rapol works in the areas of distributed quantum information processing using atom-plasmon coupling. He has also demonstrated the Bose-Einstein condensate, and in fact, I am one of the, I would say, lucky individuals who has seen the excitement that was caused when he demonstrated the Einstein condensate in his own lab at IISER Pune. I'm now happy to introduce the third panelist, Professor Rajamani Vijayaraghavan from TIFR Mumbai. Professor Rajamani Vijayaraghavan is a faculty member at the Condensed Matter Physics and Material Science, Tata Institute of Fundamental Research, Mumbai. He currently heads the Quantum Measurement and Control Lab, wherein the main goal is to develop techniques to stabilize quantum states against decoherence. His current research interests are in the field of quantum error correction, quantum simulations, and quantum limited parametric amplifiers. The panel discussion is moderated by my colleague from Physics Department, Shubhro Sen-Gupta. He is a theoretical condensed matter physicist specializing in the field of strongly correlated electron systems. His research interests lie in modeling of electronic and magnetic properties of strongly correlated systems, X-ray spectroscopies, spin and orbital magnetism, and magnetocrystalline anisotropy of nanostructured materials. So I hand over now to Shubhro to conduct this panel discussion, which is going to be about Indo-French cooperation in the field of quantum technologies.
Am I audible? Is the mic on? Okay.
I take this opportunity to wish you a very good afternoon by now. It gives me great pleasure to welcome all of you to this very interesting panel discussion, the Indo-French cooperation perspectives in quantum technology, and of which this seems to be a microcosm. I have been given the opportunity to moderate the session. So a brief introduction about myself. I am a theoretical condensed matter physicist, and I study strongly correlated electron systems and disorder-induced chaos, quantum chaos in such systems, where very strong Coulomb interactions amongst Avogadro number, which is 10 to the power 23 electrons, result in a highly correlated soup, so that individual electrons completely lose their identity. This results in exotic emergent phenomena like high TC superconductivity, the quantum Hall effects, quantum magnetism, etc. Such strong interactions may conspire to give rise to experimentally detectable pseudo or quasi-particles that may have only 1/3 of the electronic charge, for example. Now, this is a somewhat different direction, so-called many-body theory, at least superficially I should say, compared to the achievements of Professor Haroche, who revolutionized the non-destructive measurement of single quantum particles. However, at the heart of both fields is quantum mechanics. So before we start the panel discussion, I would request each of our distinguished Indian panelists to best represent their area of work in terms that may be somewhat understandable to our young school and undergrad students here. So let me start with Dr. Sinha.
So thank you very much. It's working? Yeah. So thank you very much. And of course, thanks to the organizers and Shiv Nadar University for thinking of me to join this very esteemed panel discussion. It's an honor to actually be sitting on the same stage as Professor Haroche, who is used to this sort of thing by now. Since Friday, we have been seeing each other once in a while, and so by now, I think he must be thinking that, okay, we'll move on with the discussion and not thank him anymore, but we cannot help that. We are all very young people here, and we are here because of people like him who have pioneered so many activities that enable us to do what we are doing today, the little that we are doing today. So thank you very much for being here and for joining us in this. So a little bit about myself. Well, of course, it is always difficult to go first in introducing. So I will keep it to a certain short level so that the others also follow that, right? So then we move on to the more interesting elements. So I am, of course, Urvashi Sinha. I'm a professor at the Raman Research Institute in Bangalore. I head the Quantum Information and Computing Lab. And of course, I'm very pleased to say that I actually work with one of the aspects which was discussed in the morning. So I work with single photons. So we have photons and atoms which come together for light-matter interaction, and I am specifically working with the photonic aspect of the problem. So I work with photons, single as well as entangled photons. And while we have all these technologies that we have been discussing and so on, I'm again very pleased to say that I have been able to do a large amount of our work in the lab is dedicated to understanding fundamental aspects of these problems. So we are trying to understand these photons, to manipulate them, to understand their properties better. So we are studying static and dynamic properties of quantum entanglement. We are working on quantum measurements, different kinds of measurements. We have our own methods of non-demolition measurements, negative result measurements, even generalized measurements. So these are all things which we are studying, which maybe directly are not relevant to the computing or communication. But of course, if we understand measurement better, if we can preserve entanglement longer, then naturally it has ramifications in computing, communication, sensing, and so on. But then having said that, we are in a sort of situation because we started the first lab in India, which is working on single and entangled photons. So there is a lot of interest in also looking at the applications. So we have a little marriage between science and technology happening. So whenever something interesting scientific comes out, we are applying it to technology. So to take an example, what we have done last year, and of course we published it last year, it was done a few years ago. Publication takes time for the students who are impatient. So we did the first loophole-free violation of what is called the Leggett-Garg inequality. And so this is the time equivalent of what we have heard a lot about, which is Bell inequalities. That was, in fact, the loophole-free Bell inequality was given the Nobel Prize this year. And so the loophole-free violation took us a long time. But then, you know, we did this with the intention of actually coming up with an experiment which does not have any, you know, fault in it. That is loophole-free in a general term. And now that we have this, this can be used as a test bed for secure quantum communications, which is what we are looking at, for generating new kinds of random numbers, for coming up with new protocols where the security is better, let's say, than the, you know, currently existing counterparts. So secure quantum communications is one of the areas which we are looking at a lot. Because, you know, photons lend themselves to communication. So photons are chargeless and massless. So they can really go a long way without interacting with something else. And it is a personality trait that I have inherited from photons, I would say. So it's a good thing to, you know, have in an Indian scenario and not be bothered by perturbations around you. And so I work with photons and become a bit like them, right? So these photons we are using for quantum key distribution. So what is it? So students may not know. So you are using a credit card, you're using online banking, and nowadays maybe you have credit cards even if you are not very old. I mean, people like Vijay and I probably got credit cards much later. But then, you know, now it's very, very easily available. So you are actually trusting someone. So you're giving this information and you're trusting that entity, that it doesn't go to Rupamanjari, who is of course a very honest person, but suppose she takes away all the little money I have in the bank, we have a problem. So how do you handle this? So this is called classical cryptography. It was mentioned earlier. But the problem is, of course, our friend, the quantum computer, which Vijay is working on, which may actually solve, you know, the factorization problem and break your Shor's algorithm and so on. It won't happen today. As Serge mentioned, it'll happen probably several years down the line, but we need to be prepared from now. And so we are working on techniques whereby we can replace the whole paradigm using quantum mechanics to come up with what is called secure quantum communications, where we are using laws of quantum mechanics to secure this and not based on what it currently is based on. So that is quantum communications. We are very interested in increasing the distance over which this happens. So we have a project with the Indian Space Research Organization, which is India's first project on satellite-based quantum communications. So we are trying to, you know, maybe hopefully we can communicate with France, but we are already going to perhaps communicate with Canada for this 13,000-kilometer link. So what is the point of communicating if only, you know, Rupamanjari and I are communicating with each other in a secure way? We hardly have anything secret to share. But then it is for the military, it's for the banking. But then, you know, these are the applications which excite us. But what we are doing is coming up with new ways of manipulating entanglement to have more robustness in the protocol. Our interests are more scientific in nature. So we're coming up with new protocols, new ideas to, like this Leggett-Garg violation, to come up with new ways of handling this problem, and in the same time also coming up with methodologies of increasing the distance through relays, quantum repeaters, quantum teleportation, something the students maybe have, you know, are familiar with, beam me up, Scotty being a very popular thing from Star Trek generation, which is our generation again. But then having said that, we are at least able to beam up the state of a photon and transfer it somewhere else. And so these are all things which are, you know, sort of connecting basic science and technology, and which is what our focus is. Quantum sensing is another focus area, but looking at it from a perspective of weak measurements. Not quite necessarily directly as a quantum sensor, but studying measurements to come up with better sensing. And then, of course, the other area which we are looking at is quantum computing, but not the traditional superconducting qubit or the atomic qubit. We are looking at higher dimensional systems of the single photon itself. And again, that is exciting to us as scientists because it's not a solved problem. So lots of new areas we could do. And that's where we want to continue, you know, doing new things and then transfer it to people who may be able to commercialize things better. So that sort of sums up my photonic journey.
Yeah.
Shubhro.
Then on to Professor Vijay Raghavan.
Thank you. I'll be brief. It's a pleasure to share the stage with you, Professor Haroche. To summarize my area of work, Professor Haroche actually mentioned this in his speech. I work with artificial atoms. So it might seem surprising that even though quantum mechanics was originally invented to explain the sort of the atomic world or the world of photons, it turns out that if you do things correctly, you can see those effects at a much larger level. And the systems I work in are essentially electronic circuits using superconducting materials, which under appropriate conditions of very low temperature and proper shielding and isolation, behave like atoms in the sense that they also have quantized energy levels. A simple way of actually understanding some of the simplest types of artificial atoms is just like a quantum version of an oscillator. So these are oscillators which oscillate about 1 billion times a second, so they're in the microwave regime. And the quantum states are the ground state of that system, that is basically when the system is quiet, and when they're oscillating with the 1 quanta of excitation, which is the smallest amount of energy you can impart to this system. There is also parallel with the atom-light interaction, because we now have, instead of atoms, we have artificial atoms, and instead of conventional optical light, so light at optical frequencies, we have microwave light. So all of these things are actually electromagnetic waves, just different frequencies. So the physics is actually the same. But some of the parameter ranges in terms of how strongly things can interact, that changes, and that allows you to look at new areas of physics in light-matter interaction, which is not possible in a conventional atom-light system, but it's possible in these artificial atoms interacting with microwave frequency radiation. Just a couple of examples on the kind of projects we are working on. One of the things we are trying to do is trying to reimagine what a qubit should be. As I just said, a qubit can be thought of as an oscillator. So one project we were working on is looking at more complicated circuits, and this is one of the advantages, that since these are electronic circuits, we can build them in different ways using the elementary composite particles. You know, it's maybe a bit of a stretch, but it's sort of like saying that if you had protons and neutrons and electrons in your hand and you could put together to make new kinds of atoms, we can sort of do that and essentially create systems which have different quantum mechanical properties. So we are looking at systems which have more than one way of oscillating, and each of those ways can be treated as a qubit. But because they are all part of the same system, they interact with each other, and that gives you a new multi-qubit type of system. And another area we are focusing on is to create small networks of qubits which are connected very strongly with each other. At the end of the day, a quantum computer is really a collection of lots of qubits which all can interact in a controlled fashion. But because of practical constraints, it's actually harder to create interaction between qubits which are physically far from each other. So we are thinking of ways of how to do that, where the distance between the qubits doesn't matter so much, that you can create interaction. And these things can simplify how you execute any quantum algorithm on these systems. And slightly more on the technology side, we are also involved in one project to build a 7-qubit quantum computer. You know, it sounds like a very small number in today's world where you're hearing 50, 100, and 1,000, but you have to get started somewhere. You have to get your hands dirty to actually build one of them. So we have one project in collaboration with the DRDO, which is the Defense Research and Development Organization, and Tata Consultancy Services, to build a full system using these superconducting qubits. Thanks.
Thank you. So let me now proceed to Professor Rapul. You have one, okay.
Hello, can you hear me? Yeah, so thanks to the organizers for giving me this opportunity to share stage with the stalwart of quantum mechanics. So thank you very much. Yeah. So yeah, couple of things I would like to take you from what Professor Haroche said in his talk. So, okay. Yeah, so he talked about how quantum mechanical systems decohere and how it's an impediment for many of the applications that people are envisaging to build quantum computers. And also he talked about building better and better sensors for things like measuring time, measuring accelerations, measuring rotations, etc. So in my lab, we use ultra-cold atoms and ions for doing a variety of things, starting from understanding the basic, doing basic science to some technology development. So about talking about basic science, we have used ultra-cold atoms to actually study how these quantum mechanical systems decohere when they couple to an environment. Because all the quantum mechanical decoherence is finally coming about because these delicate quantum systems are interacting with the environment which you can think of being a mess of all random oscillators everywhere, and then your quantum system is kind of getting coupled with this, and it's basically losing the coherence, the property of coherence that exists within that. So those are some of the things that we have studied in the past. Now the other thing we are looking at, studying and also trying to develop new technology, systems for technological applications, is exploiting the wave-particle duality nature of particles. So if you start, at a macroscopic scale, we all are classical objects. A cricket ball, etc., is a classical object. The fuzziness that's associated with that, the so-called wavy nature that's associated with that, the wave nature, it's kind of so minuscule at the scale of things that we are able to measure. It's completely, at the moment, impossible to measure. However, if you go to scales where the particle sizes are of the scale of atoms, etc., then you start seeing the waviness associated with the particles, the wave nature of these particles, to be very significant in such a way that it starts, your atoms stop feeling like material objects. They start looking like waves. And this is a very important property that is actually utilized for building some of the sensors. Like, for instance, you can think of, instead of using light, you can think of using atoms to build interferometers, like a Michelson interferometer or a Mach-Zehnder interferometer that we study in college. Those are those things you can actually build with atoms now. Now, of course, these are things that have been developing now, but this wave nature has been utilized in the past when people didn't talk about quantum technology, like, for example, the scanning electron microscope, etc. They did use the wave nature of they do use the wave nature of electrons to actually beat the diffraction limits of light, because the wavelength of visible light is approximately half a micron. However, if you go to electrons with very high energy, your wavelengths can go down to several angstroms. Now, using that, you can actually go and image objects which are in the range of several, nanometers or several tens of nanometers in size. Now, yeah, so coming back to what we are utilizing this wave nature for is to actually build, say, an interferometer with the light, with atoms, to actually measure local gravitational acceleration very precisely. Now, in school, we study that gravitational acceleration is 9.8 centimeters per second square, right? But if you actually do a very, very careful measurement and go up to like 7, 8 decimal places, then you start seeing the effect of at what latitude you are measuring this, at what height you are measuring at a given place, or whether the moon is going over you or not. All these start affecting at every different decimal place, including you come to a situation where if people are moving around you, you can be sensitive to motion of people moving around you. So this can be this kind of devices can be very, very useful for modern day applications. For instance, one can actually measure the shape of the Earth and the geoid, what it's called, very precisely, map the entire, by moving this instrument around, you can map that. And for things like strategic applications, you can probably detect a tunnel underneath you without actually using electromagnetic waves. So the enemy can be blind to such devices if he tries to, if you use electromagnetic waves, he can actually figure out there is somebody seeing from top. But if you use such a gravitational, gravimeter, then you can actually, the enemy will be blind. So not only that, for instance, you can map changes in underground water table changes over seasonal changes or over years, how it is changing by such sensitive devices. The other thing that we are looking at is how to build these interferometers with not just a bunch of atoms which form a giant matter wave when we take these atoms into this Bose-Einstein condensed state, which Professor Haroche was talking about. You can actually think of creating something equivalent of lasers, which is of photons, with atoms. Colloquially it's called as an atom laser, but it's a coherent beam of atoms, essentially. Things like that, you can think of generating a so-called atom laser, in quotes. And then think of doing more better and better sensors, building better and better sensors with these coherent beams of atoms. The other thing that is another aspect that is going on in our labs. And one more thing that we are trying to build is, we are halfway through building, is these very extremely precise atomic clocks. And at the moment, the world relies on what is called as a microwave frequency standard at around 9.2 gigahertz, I think, which is based upon some transition in cesium atom, which is measured again using cold atoms. But the world is slowly going to move to optical frequencies, because if you move from microwaves which are in the range of 10 to the power 9 hertz straight to frequencies or light which is in the range of 10 to the power 15 hertz, you immediately gain a 4 to 5 orders of magnitude better precision than microwaves. So world is going to move towards that. So when that happens, there have to be enough number of these clocks spread across the globe so that a particular atomic system can be adapted as a standard. So people are working, building clocks with strontium, with ytterbium atoms, with ytterbium ions, aluminum ions, and all, like 6 to 7 such species, but we don't know which one will become the final standard. Now, that is something which also we are building. Now, these clocks, as Professor Haroche mentioned, they are so sensitive that they can detect gravitational redshift over a few millimeters. If you take this system, move it by a few millimeters away, you start seeing the shift in frequency. So these are applications of these clocks for fundamental physics. But at the same time, these clocks can be used for GPS navigation, where you get precision, I don't know, maybe of order millimeters or so on ground if you measure these frequencies very accurately. And on the other hand, these clocks also can be used for fundamental studies, which have very high, huge implications even in particle physics, etc. Like some of the constants that we take them as granted as constants, like the fine structure constant alpha, etc. These are not really constants. Constant is what people predict. They do vary to some degree, which is very tiny to be measured. But once you have such clocks, it becomes easy to test such theories which predict such variations of these constants, which would have huge ramifications in tuning and tweaking some fundamental models of physics that we currently know. So yeah, that's about it in the kind of different experiments and the work that goes on in our group. Of course, we are also building a neutral atom quantum computer and an ion trap based quantum computer. That's more for the quantum computing part, but as we all know, we don't know when a real quantum computer will come up. Yeah, thank you.
Thank you. So before proceeding further, I feel almost obliged to mention my connection with light-matter interactions. The whole of my PhD and much of my postdoc were actually sort of devoted towards modeling of cold-level X-ray spectroscopies from synchrotrons, as well as resonant and non-resonant X-ray scattering data from correlated systems. So I indeed feel very honored to be on the same stage as the legendary Professor Haroche. So, so the catchphrase of today's panel discussion, quantum technology, may seem somewhat contradictory, even oxymoronic to the beginning undergrad or high school student or the common man. This is because the word quantum conjures an image of a very philosophical and esoteric branch of theoretical physics that concerns the invisible submicroscopic world where all classical intuitions seem to go completely haywire. And as Bohr puts it, those who are not shocked when they first come across quantum theory cannot possibly have understood it. Apparently, it has very little to do with our day-to-day lives. On the other hand, technology seems to be a very routine applied branch of science whose achievements we use regularly in our day-to-day lives in form of cell phones, computers, the internet, and whatnot. So superficially, the two seem to have little connection. However, one must remember that what is fundamental science today becomes technology tomorrow. In fact, most of our electronic gadgets, which are mainly semiconductor based, use quantum mechanics for their design and operation, which a model undergrad physics major student only realizes by the end of his third year or so. Thus, in view of the fact that quantum mechanics was already in wide use since the beginning of the semiconductor era several decades ago, I am very keen to know the views of Professor Haroche on my first question. So what does the new phrase quantum technology really mean in today's context, and how is it different from the already prevailing use of quantum mechanics in technology?
Okay, so, that's a big question. I would like first to make a remark after the different speeches we heard. I think one common thing about all this research is that all of you have a passion for what you are doing. It's quite clear from the different descriptions that you gave us that you are motivated by curiosity and by passion, and the fact that there will be application later on comes second to that. And this is the case. This has been the case since the beginning of science. For example, you mentioned the fact that you can measure now the gravitational field with a very high precision, and this gives us an indication about the shape of the Earth and about the very important details about that. This has started in the 17th century, in fact. There were people who were carrying pendulum clocks over different places of the Earth, and they realized that the pendulum was beating slower at the equator than in the northern hemisphere, and this was the first measurement of gravitational effect linked to the measurement of time. At that time, people were doing that just out of curiosity, but they also understood that in order to get funding, you have to find some usefulness. And so Maupertuis, who carried the first measurement of the shape of the Earth using this kind of methods, said in the paper at the French Academy of Sciences, this might have interesting application for navigation. And in fact, it's what we are doing today. The GPS is an application for navigation of very sophisticated techniques. At that time, the clock had a precision of, the clocks were beating at 1 second period, and they had a precision of a few seconds per day. Now we have clocks which have a frequency of 10 to the 15 seconds, as you said, and the precision has increased by 15 orders of magnitude too, and now we are talking at the femtosecond per day. This is just a qualitative change, but a quantitative change, but I mean qualitatively, the passion was the same at that time and now. Just use science to achieve things, to solve problems which are based on our curiosity, and one day it has an application for technology. Now the question what you ask is what is the difference between the quantum technologies that we had in the 20th century and what we could do now. Basically, the quantum technology that we have in our everyday life, which is, for example, the GPS, the atomic clocks, classical computer, are based on statistical properties of system. The inner properties are quantum, but the quantumness is veiled when you look at macroscopic system. You don't see the effect of quantum jumps. You don't see immediately quantum superpositions. They are just phenomena which explain the structure of matter and the nature of light-matter interaction, but they are not using quantum logic at the heart of the phenomena. Now what we can do, since we have been starting doing 20 or 30 years ago, is to manipulate single quantum objects, either natural objects like atoms or artificial objects like the one which were described superconducting devices. And this allows us to try to extend the usefulness to the quantum logic, that is to use state superposition and entanglement to achieve things. It's a formidable, difficult task because of decoherence, but there are hopes that useful things will come out of that, and that's what we're discussing. But you were right to say that the quantum nature of the world is important at all levels of technology today. Not only the technologies which will use of quantum logic, but the one which were used on the quantum structure which were making use of the quantum structure of matter and the interaction of matter with light. So I don't like too much this denomination, first quantum revolution, second quantum revolution. All this is part of the same evolution, trying to understand deeper and deeper how nature works using the laws of quantum physics and the laws of quantum logic. You mentioned also, one of the things interesting that you mentioned is the fact that these experiments could also maybe help us to understand much deeper problems relating gravitation to quantum physics, that is to tackle cosmological issues. It's quite clear that now the quantum measurements are so precise that you can see gravitational effects at the level of millimeter distances. If you extrapolate this, if you start to think about atomic clocks which should be able to see gravitational effect at the size of, at the scale of a single atom, which involves increasing the precision by 4 or 5 orders of magnitude more, then you will have deep questions about quantum gravity which will come into play. If you have to, you would have to understand what happens when gravitational effects become important to describe the structure of atoms. If you reach a precision such that you will be able to see that. You can also start thinking about thought experiments. What would happen if an atom is close to a black hole? What happens if you have an entangled system made of 2 atoms or atomic photon, and one part of the system falls inside the black hole? What happens to the information? Of course, we cannot do experiments, but if you think about experiments, thought experiments, it might help you to understand deeper what happens. In fact, when Einstein and Bohr discussed quantum physics back in the 1920s, they spoke about single photons, single electrons, but they thought this experiment would be forever impossible. But it helped them to understand what quantum physics was about. And I think we are now reaching the point where, by imagining experiments that you cannot do, but you can imagine them, will help us to understand deeper about physics. In fact, the problem when you do a thought experiment, when you imagine a thought experiment, you try to find out whether there is not a contradiction between the laws of nature, what happens in a situation with respect to quantum physics and gravitation. So what Einstein tried to do was to challenge the quantum concept by trying to imagine experiment which will give result in contradiction with quantum physics. And I think, and of course he failed, and in fact quantum physics has resisted up to now. But if you start asking this question in connection with between quantum physics and general relativity, you might have interesting you might find interesting things. And I think this is a point where cosmology and quantum physics get close together. And this is one of the challenges in the future. This is very far from practical applications today, but you never know what will happen in the future.
Okay. So, so just to kind of reiterate what you said, I mean, would I be very wrong if I said that the statistical properties of quantum mechanics are utilized even at the basis of normal conductors? Yes. But when we speak of superconductors or BECs, it becomes a macroscopic coherent wave function. That's an entire new level. Yes. So in that sense, the old and the new quantum technologies are also different? Yes.
Yes, you have, it's a good example. In fact, Bose-Einstein condensates and Fermi degenerate gases are examples where the quantum properties extend to a collective system. Another point I would like to stress is the fact that all this science, all this physics is connecting in a very deep way fields of physics which used to be very far apart from each other. For example, you are working in condensed matter physics. When I started 50 years ago, the course in condensed matter physics was quite disconnected from the course in atomic and molecular physics. Yeah. And now they come together. If you start building quantum simulators in which you put atoms at well-defined position, you start to observe effects in condensed matter physics with tools that condensed matter physics don't have. We can observe individual atoms. We can look at correlation between atoms. We have ways to investigate condensed matter phenomena at a different scale, and this is a very fruitful connection between this field. And as I mentioned before, you have also now a connection building up between cosmology and our kind of physics. So I think it's very exciting to be at a time when you start to see all these connections, all these very fruitful relations between the fields. And there will be applications, but we don't know. I think we cannot really predict what they will be.
Okay, thank you. So I would invite any of the other panelists to share their views on the same
Sure,
topic.
thanks. Yeah. So I would just like to quote Isaac Asimov here, who said, "Today's science is tomorrow's technology." So I think that is what sums up, all the discussions we have been having. So I mean, Serge already mentioned this earlier. So today's curiosity-driven research is going to become tomorrow's technology. But then curiosity should not be about the technology from the very beginning. We remain curious about manipulating things at a fundamental level, and technology emerges organically. Otherwise, of course, the forced technology cannot be very useful. So just to give an example to what you mentioned about cosmology, and so the LIGO is an important example here. So the LIGO, the project of observing gravitational waves through this massive interferometry. Now they are using squeezed light to increase their precision. So this is somewhere, quantum mechanics and cosmology have really already come together in a very macroscopic example. But another example I would say, which is close to my heart, is entanglement. Because earlier entanglement, as you mentioned in your own lecture earlier, has been known for a century. But then, it was something that was, very interesting. Great minds have been curious about it. Then came John Bell, who came up with the Bell inequality. At that time, John Clauser, as we perhaps know, did not first get the funding to do the project, to actually do the first Bell inequality violation experiment. And there's a whole interesting story about how he ended up doing that. And then there's this series of experiments from Alan Aspect and his collaborators and Zeilinger and so many other people who have come up with now this loophole-free violation of Bell inequality, which has given this big boost to quantum communications. So when John Bell came up with, wish we could go and ask him. He kind of passed away too early for all our liking. But then, I'm sure he did not think of security in communications as something he would be, revolutionizing. But then that is what has happened, and that is where we are now. So I think this is the difference, in my mind, that earlier all the examples you took were based on certain statistical properties, but now we have this capability of doing experiments which were imagination in the last century. And that is perhaps what is the quantum technology today, because this imagination is now becoming real experiments, right? So Vijay, you want to add something?
No, I think
fine.
Umakant.
I would like to add something, to make a remark. When you talk about the connection between the opposition between basic science and applied science, from politicians you get often the answer, okay, that's true, but we should concentrate on application because there are societal needs that we have to fulfill. It's very important, and basic science costs a lot of money, so we understand it's important, but let's import the result of basic science from abroad and do only applied science. And I think this is also wrong, because the way to attract bright minds and bright young people to science in general is to excite their curiosity and to tell them about the big challenges of basic science. And this is very important. Then you motivate them, they come into basic science, and after that they understand that basic science has to be applied. So even if you understand the usefulness of applied science, in order to do it, you need to have a basic science substrate
mic. So, so I would like to, ask you in the view of our several, young audience, what motivated you to take up a career in science and later to specialize to this kind of a field? Where you initially decided from your school days that you wanted to pursue science?
No, it has been alluded to in the very nice introduction I got at the beginning. I was, from my childhood, I was really very strongly interested by mathematics and by astronomy and astronomy, I would say. I was 15 or 16 years old when the race to the moon started and the first artificial satellites were launched, and I was amazed by the fact that I could compute the properties of satellites, escape velocity from the Earth's gravitational field using Newton's equations, and the fact that physics could be explained by mathematics, which is, of course, well known, was amazing. And I am still surprised by the fact that the mathematical theories, mathematical concepts which were invented much before one thinks they would be useful for something became useful in physics. And this is also part of the same discussion we had before. Basic science starts in physics, at least with mathematics, and the mathematics seems useless at the beginning. For example, why group theory, why complex numbers, why non-Euclidean geometry. So it's at a deeper level, the connection between basic knowledge and application can be found. And so I had this kind of intuition that it would be interesting to use mathematics for doing physics. Maybe one of the reasons was also that I had in my classes friends and young colleague students who were stronger than me in mathematics. So I did not want to do abstract mathematics. I said I have to do some mathematics which will be useful for physics. And then when I entered into École Normale after graduating from high school, I had two lucks. One luck was two pieces of luck. One was to be exposed to charismatic teacher like Claude Tanucci, who introduced me to quantum physics and to relativity. And I understood that math was not only useful in astronomy, it could be useful also for the microscopic world, and I got into quantum science. And then also the other luck was to come to this at the time when the lasers were invented. So the laser was an amazing source of light, and with Claude Tanucci, we had the intuition that it would revolutionize atomic physics. We did not know exactly how. I remember one day he came in my lab with a paper by Ashkin. Ashkin was a guy who was working at Bell Laboratories, and he wrote a small letter in Physical Review letters saying that you could use laser light to manipulate the external degrees of freedom of atoms. It was the beginning. It was the idea of laser cooling, in fact, and laser trap, using light to trap atoms. In fact, Ashkin was one of the founding fathers of this field. He got the Nobel Prize 3 or 4 years ago for the atomic tweezers. He was 96 years old when he got the prize. So it tells you something about the delay, which can, you have to wait between you make some kind of discovery and when it is recognized. And I think for Ashkin it was a little bit too old. It was extreme. But so Claude came in the lab and showed me the paper by Ashkin, and we started wondering. At that time it seemed completely fantasy, like the Asimov kind of story. The lasers were very, very far from having the properties required for that. But I have witnessed during my career in science how the laser has evolved, and I must say that one of the pleasures you have as a scientist, not only to make discoveries by yourself, but also to be able to witness what colleagues all over the world are doing, and it's a big privilege that I have had, and I'm sure it will go on in the future because a lot of surprising things will happen with the evolution of technology and with this connection, fundamental connection between basic science and technology. What I also want to say is that it goes both ways. I have insisted upon the fact that technologies come from basic science, but on the other hand, as you mentioned, technology is also helping basic science. For example, the discovery of gravitational waves and all the opening of a new field of astrophysics has been made, comes from technology. So it's a kind of virtuous loop. You have a connection between basic science and applied science, and it goes both ways. And we have to go on in this direction.
Thank you. The next question, I'm sorry, is again to you. So basically, Nobel Prize somehow marks the zenith of success that one can achieve in one's career. So you're, of course, one of the most successful individuals. And people seem to think that successful individuals have not faced failures, at least young people, and they're terribly afraid of failures. So what are your views on failures and how to, how to view them, or how to, get some kind of an inspiration from them?
First of all, I would like to make a comment about the first part of your question. The fact, the fact to get a Nobel Prize is based on achievement, but also on luck, because there are many, many people who deserve it at the same level with the same standards. And if you take, when I got the prize, I got it with Dave Wineland. I think one of the reasons was that we were doing some kind of mirror image experiments. So the Nobel Committee found that it would be nice to emphasize this point, that I was working trapping photons, he was trapping atoms, and we did similar experiments. But there were maybe 10 or 15 other people who were doing as beautiful experiments and who did not have the luck to fall into this focusing spot. And the same happened with the last year prize. It was given to 3 people because that's the maximum number of people who can get it, but other people were involved in this study of entangled photon states, and I don't want to give names, but I want you to understand that to get a Nobel Prize is a lot of luck, because you are part of a big community of researchers. Now, what was the other question? The failures. You have it happens, of course, when you are going doing experimental work. You might have some drawbacks. You might find problems. Experiment might fail, either because you did not conceive them well, or because you have accidents. For example, I remember one time we had a cryostat which blew up, and it took us 1.5 years to build the system back. So you have to really to be resilient, to stick to what you want to do if you think you have a good idea, and try to resist to this kind, to the feeling of to being discouraged by this kind of problems. I think what I found useful in my career is that I was not only doing research but also teaching. And when you teach, it changes your state of mind. It takes you away from the difficulties that you might have in your experimental work or in your research work. And also, very importantly, it gives you ideas, because when you have to teach, and I'm thinking teaching, for example, at the graduate level, when you teach, you have to understand in a deeper way what you are doing, and it might give you ideas about other experiments. For example, the experiment we did with single atoms very often came from reflection and from ideas we got from teaching courses to students. So, well, I think there are times when you have difficulties in your research, you have failures. Of course, you should not fail all the time.
Yeah,
at some point.
absolutely.
But and you should, sometimes you observe something that you did not expect. And when you do that, you have to, very often it's just an artifact, it's not important, but sometimes it's something which can give you new ideas and new directions. So doing research involves some luck, but you have to recognize when the luck comes.
Yeah, about the teaching aspect, I couldn't agree more. So I would request if any of you have any comments on failures or any personal experiences.
Stories? Yeah, we have. So I'll give you one failure story, which turned it. So the point is that, when you're doing experiments, mostly things don't work for a long, long time. And then, So one has to wait for that eureka moment when things work, and then, so I think 90% of the time it is about troubleshooting, 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 and then in the end, there's that 10% which you have been looking forward to, and that could take months, years, depending on what you're doing. So one example is an experiment I did while I was at IQC, and there my French mentor, but he's not the French, he's from Quebec. So you know you're very distinct from each other, and you acknowledge it in the public domain. So my French mentor, I would say Ramon Laflamme, so he said that, it's this great experiment you've joined, so I know you're in from nanotechnology, but let's do this experiment in quantum optics. It'll take you 3 months. It's a perfect experiment, very excited. All the theorists and him, they were all excited, and I said, sure, it is exciting to test Born rule for the first time, test for Born rule as a precision experiment. 3 months, 9 months, 1.5 years, people who were associated with the experiment, along with my colleague Christophe Coutu, who is from France again, they left, they went on to different positions. But it's not because I was not, no, just to say that it's not that I was inefficient or particularly bad in doing experiments, it's just that it was a precision experiment. It took its time, right? So second year down the line, I'm in Ramon's office. What will happen to my career now, do you think? 2 years, no publication. What is going to happen? And he said, he was very, very jovial. He said, don't worry. When this works out, it'll be perfect. You just carry on, This optimism is something that is infectious. Maybe it's a French quality, I don't know. But then having said that, it worked after 3 years. So that's how he ended up being so lucky, right? I mean, apparently it's about luck, but it's not just luck. So he's just too humble. So 3 years, the experiment worked, and of course it was a eureka moment, but it took 3 to 4 years to get those results. And of course, now it is the first experiment to test Born rule, published in a very important forum. People do care a lot about it. So, one has to persevere. So it is not about instant gratification. Then, of course, we are in the wrong field altogether. And so that is my failure to success story for one experiment. So Vijay, you have a failure?
I mean, I don't have a particular example, but I often tell this to my students that, maybe I shouldn't just call it failure, but for most of the time, that's what you'll be doing. And I often find that that process is actually a lot more enjoyable once everything works out. And then sometimes in hindsight, you don't think too much about the result itself, but the process of actually getting there, all the things you solved along the way, that actually is probably most of your research life. And if one can figure out a way to enjoy that process, I think those results will come and you wouldn't worry about all the so-called failures along the way. So I found that to be at least true for me for most of my career so far. And I try to tell this to my students also. I mean, I guess as Urvashi was encouraged, one tries to give the big picture, and you're always learning, even if you're not getting. There are experiments which do fail, but you do learn something from them.
I mean, if you allow me, I would like to state one example which my research supervisor gave me of his experience in MIT, which basically guided me and has been helping me to get over this 95% times of failure that you experience in the lab on a daily basis. So the example was in 90s, there, these days, these air conditioning units, they keep coming with a label called inverter technology and all that. But this actually came in late 90s. And anyway, I shouldn't reveal the suspense immediately. So they were doing some precision measurements with trapping individual ions in there's some trap where there is strong magnetic field and some electric fields. You catch these in free space. They're called penning traps. And doing some very precise mass measurements. Now, at some point, they started seeing some weird signal in their experiment, which is like, I don't know, about 100 times larger than what they expect from this mass signal that they see in this, by these particles moving inside this trap. Now, they went over everything, opened the cryostat many, many times. This went on for 6 months, 8 months, and then daily the same story. They would just come, see the same thing, and no idea what is happening. Nobody in the group has any idea because there are people who have been in that field working for over 10 years, 20 years. Nobody has any clue. So daily they would come try something, go back home completely disappointed. Now one day they and then they put this picture of this bad, the wanted guy, or the spectrum of the signal all over the building, just to hunt for if there is something that is coming from outside. This is more or less sounding like some, I don't know, magic, black magic which somebody is playing on you. So they, on some coffee table conversation, somebody was talking next to them and saying that, oh, we installed this very high-tech air conditioning unit on our floor. And then it turned out that that thing was right above their lab, and it was this inverter technology which was basically switching the speed of the motor as and when the power was needed for their, for cooling. And then that was showing up as some signal which was basically ruined their entire, I think about 8 months of their time. Now, this is an example where cause in the lab, that are caused in the lab. That is, I think perseverance is one important thing, and then being creative is another thing I would point out.
Okay, so I would, urge you to look up this very famous Einstein quote on this regarding the discovery, the final discovery of E equal to mc square. There's a very long quote. It's an assignment to the audience. And I would just say that, face your fears. Unless you face your fears, you'll never be able to overcome it. So when I was first asked to moderate this session, I said, oh my God, on the stage with a Nobel Laureate, it's too difficult. But then face it. Okay, so before we go into the last topic of Indo-French collaborations, let me ask this question. So basically a lot of beginners who want to go into experiments feel that for doing experiments, they don't need to know as much so-called fundamental science as theorists do. So this seems to be a myth. And is it partially true, first of all, also elsewhere? And secondly, what are your thoughts on this as an individual who had to understand quantum mechanics inside out in order to finally arrive at your path-breaking experiments?
What you just said reminded me of an advice I got when I went for a postdoc. I went in the lab in Stanford, the lab of Art Shallow, one of the inventors of the laser. And he used to say to the young people coming into his lab, to young postdocs, who were somewhat inhibited by all the knowledge they did not have yet. And when you start in science, you have a lot of things to, you think you have a lot of things to learn, and you might be blocked or inhibited by all the knowledge which has accumulated before you. And Art Shallow used to say, you don't need to know everything. You need only to know one thing that other people don't, which is very easy, which is very easy to say, but more difficult to implement. But that means that if you work in a given field, you might have an idea that other people did not have before you. And if you are lucky, this will give you an advantage. Maybe I can also react to what you just said. We are talking about failures and luck. And there is a very famous example of that. In the 1960s, people working at Bell Labs were trying to develop a new antenna to detect radiation. And they had a strange noise in their device, and they didn't understand. It was like the noise you were mentioning with the cooling device. And at first, I thought that the noise might come from pigeon dropping. So they were cleaning their horns, cleaning their antenna, and they didn't understand what was going on. And then someone suggested that maybe they were detecting radiation from outer space, and it was that. So they were lucky. They had to overcome a problem, and it was the beginning of radio astronomy. It was already, in fact, what they were detecting is a cosmological background radiation, which of course opened a huge field of research in astrophysics. So you have to have failures and luck, and when you are lucky, you have to recognize the luck, which is the most important, difficult part of it.
Okay. So finally, let's move on to the topic of Indo-French collaborations in the field of quantum technologies. So I would like to ask the panelists about their, involvement in any such projects and how such a collaboration between experts on both sides have, may help in the development of a rapidly evolving field of quantum technologies and so on. And maybe in the end, Professor Haroche may sum up. So maybe I can start with.
So you mean
Urvashi?
Indo-French in particular?
Yeah, in this context, but also in a broader sense, like he mentioned, everything has to be, in some sense, like the CERN, meaning ultimately if there's a very big.
Yes, yes, yes. So well, so far as my own personal Indo-French thing is, as I already alluded to that in the beginning, in the last discussion. So I have been very lucky to have a French mentor at my postdoctoral level. But the person I worked very closely with, who was also a postdoc at that time, Christophe Coutu, who's currently in University of Troy, and he's heading, the group there on nanophotonics and so on. So we've had very successful, collaboration on this particular precision experiment. But now we are looking at new avenues to collaborate with our very, different technologies that we have for making photons. So he's working on solid-state emitters, whereas we are looking at spontaneous parametric down conversion. So we have lots of ideas on how we can make these talk to one another, and starting at a ground level and then going forward towards any possibilities on distributed networks and so on. But then the collaboration that I have been continuing for the last several years is with Professor Alex Mashkin, who's at, please pardon my pronunciation, University of Sergi Pontoy. You know what I'm talking about. So it's a part of CERN, it's not CERN, it's a part of CNRS. It's one of the CNRS labs, and Alex is actually a very well-known theorist who works on different types of quantum measurements. And so together with Alex, we have been realizing many interesting experiments in our lab at RRI on different ideas towards making measurements more generalized, not the strong von Neumann measurements, but using what is called generalized measurements. So we've had a very successful history of collaborations. We also got funding from a US funding organization earlier. But then, of course, we are looking, we'll be very happy to look at opportunities which emerge if they do, because panel discussions usually end with a discussion. They don't have much happening tomorrow, for instance. So I would really hope that this discussion actually leads to something positive emerging out of all this, because it's rather clear that we have excellence in France in quantum technologies. And I wouldn't say that we have the same critical mass here in India, but at the same time, we are doing things with a lot of passion. And whatever we are doing, I would say, is aimed at a very high precision level. So a collaboration between India and France, more formal structure for that would definitely be beneficial to both countries. It wouldn't just be because of the French expertise, but I think we also have a lot to share that we would want to, given a certain platform. So yes, I have known many French people, but I've also collaborated formally with many of them, and some of them continue today. And I'm very hopeful that we can have more formalized structure going forward.
And if you could also comment a few lines on the future of quantum technology in this respect. I mean, what do you see as the future of quantum technology?
One of our earlier secretaries of the Department of Science and Technology used to say the future is uncertain, that's why future is quantum. So, so that was a very quotable quote. So it's very difficult to comment on future of a subject which is, based on, ideas which are still evolving. So, and of course, in a discussion where we have Professor Haroche, who's, made it rather clear that, we are at a level where we are, irrespective of our particular, age, which is not the same as the last bench people here, but at the same time, it is it is curiosity which is still driving us. But we are looking at lots of very interesting possibilities today, which probably we weren't looking at few decades earlier. And one of them, some of them are at a much higher level of being practically useful, if that is the word that, the higher ups like. So one of them would be in the sensing domain. One of them is, of course, in the communications domain. So secure communications is very much a reality. We need to solve many problems to make it much more accessible. But sensing and communication, and then followed by, I would say, sorry Vijay, but then, you know, the large scale quantum computer would probably be the one which is a little bit further down the line. But all these are possible now, and there is, so, you know, so I don't want to, you know, I mean, I'm kind of in that middle age group, let's say, where I don't want to, I'm holding on to my childlike curiosity. But then, you know, he's here, and he's a little older than me, and he's still holding on to his childlike curiosity. So I think this is what we want to do now. We don't want to necessarily speculate whether we are going to have, as an Indian, you know, India is going to have its 100-qubit quantum processor today, and then suddenly somebody says, oh, but somebody has done 400, then now let's ditch the 100, let's aim for 1,000 tomorrow. So it's not like that. It's not just a number game. There is merit to actually having certain capabilities as a country which we want to be self-sufficient in, but we don't want to get to that level where we stop talking to others. Because, you know, it is, while it is a global community, by talking to various people and, you know, agencies, overall we'll progress as a community. And just wanted to add one line here, because you've just reminded me with this future thing. There is something which is coming up, a bit utopian I would say, but then it's still very much happening right now. It's called the Open Quantum Institute, which is happening in Geneva. And this is being, you know, sponsored by the United Nations, and I'm a part of the you know, advisory board and the core task force for this. And so the idea behind this is to bring policymakers as well as scientists at the same forum, so that they can actually, whatever you said in the beginning is the dream of this institute, to bring together policymakers from all over the world and scientists from all over the world in the same forum, so that they can talk to each other and find the best way forward to bring this technology or this entire ecosystem, make it global without thinking that, you know, we are giving away secrets. Maybe there are some areas which are strategic, which will remain strategic, but then there is a lot we can do together which we cannot do in isolated pockets. And so this is where the future is heading. We already have fora like this where, you know, I'm contributing, and there are many other such things coming up. And so this is what we would really like, I think, as a community, a system where we can freely talk to each other, at least at the science level. Maybe science is something we can share, technology is something we can keep to ourselves, and you know, come up with some healthy balance, I would say. So this is my
And may I
words.
say,
Yeah.
his curiosity as at his age is probably your future aspiration.
I don't want to comment on his age.
Okay.
You know, I'm in a, I'm just sharing the stage, that is enough for me. But then, yeah, you're slightly older than the rest of the panelists here. But then, you know, the point is that it is, I mean, but then the kind of stress that I am under usually because of this need to do something day before yesterday, I don't know whether I will live to see a certain age at all, but I can only hope for the best. Yeah.
Okay, wish you all the best. Vijay.
Yeah, so I've had a lot of French connection also in my past. My PhD advisor is a well-known French scientist, in fact, one of the leaders in area of superconducting qubits. I've had a successful student visitor through the Cefipra program, Nicolas, who spent a couple of years in my lab and also later on came back for a postdoc, and is actually now a faculty in an Indian institute in one of their new programs to attract foreign citizens to take up academic positions here. I think I sort of echo some of the things which Urvashi said, that there should be a mechanism for open exchange of information, and I think Professor Haroche had pointed out that there is now this negative trend of holding on, even people working in certain areas have difficulties in getting visas to go to certain places. I think some balance will have to be found out, and maybe this fora you're mentioning is one way to do that, because there is still a lot of problems that need to be solved. I think part of the reason, and I think again Professor Haroche had hinted, is that maybe a lot of overselling has led to this secrecy, whereas the scientists really know that there are still many, many problems to be solved, and those are probably solved together better and more efficiently than trying to solve them on their own. Having said that, there's also disparate levels of prior preparation, investment in these areas. Europe and US, I would say, have been working on experiments leading to present day of quantum technology for maybe the last 3 decades or so. Whereas more active research, especially experimental research in India, is maybe less than a decade old. So with our ambitious national program coming up, we have an opportunity to sort of make a significant dent, but we have to again balance solving some of the problems, because even if somebody has already done it, when it comes to technology, it actually, you have to do it all over again. Nobody gives you a blueprint on, it's not like assembling IKEA furniture. So that requires patience and also understanding that you will spend some time. Now this is from the technology development part. You'll spend some time repeating the same mistakes, but unless you get your hands dirty, you're not going to go to the next level. At the same time, as been pointed out many times in today's discussion, that especially the quantum computing part, it's not a solved problem. Even though we sort of know where we want to get, it is not a solved problem. And that means there is opportunity for even newcomers to make radical new contributions, which could completely change how a quantum computer will be built. And I think in that context, new entrants like our country can be motivated that there is possibility to contribute in a significant way and actually change the conversation, or radically change how these things are built in the future. But again, that requires some patience to realize that you're going to maybe probe around in the dark for a while, but something could come up in the future. So hopefully we'll be able to balance these things out. And Urvashi and I have also been part of, and even Umakant have been part of framing some of the ideas and policies for this national mission. And there is a big part in there for international collaborations. So I would be curious to know, maybe now or even later, what the French programs are in terms of engaging with these big programs, which are also coming up in other parts of the world for working on projects together in the future.
So, Maka.
Yeah, so I think talking about this, catalyzing these interactions between Indian and French researchers, I remember in late 90s, at least during my PhD days and even early 2000, there used to be a lot of these meetings, in the sense of like conferences or workshops, which used to happen where a delegation of French researchers from various different groups used to come to India. And then, at least in Bangalore, I have gone through 3-4 such meetings over like 4 or 5 years, where it built some kind of a networking opportunity for young researchers, students, PhD students, where the researchers from France used to get to know them, as well as the work that they were doing in their labs, which led to quite a few of us from our generation to actually go and find postdoc positions in France, for instance, and also vice versa. So there were a lot of undergraduate students who were studying in different, the 2 ENS. They visited our labs and some other labs, where they spent nice summer and also sometimes 6 months. And even now, some of them are still in touch with us because they have gone and become faculties somewhere in French institutions. So I think, okay, just for this catalyzing aspect, this regular meetings, I am not aware of if there any such meetings happen on a regular basis, which are facilitated by Cefipra, but something that one can start on. In the second part, you talked about the quantum technology, which...
yeah, if you have any visions of the future, what...
No, I think keeping aside the word quantum technology and second quantum revolution aside, I think what the current, with all the buzz that's going around, it provides us with a unique opportunity to actually do basic science as well as applied research using the same systems, because all the capabilities that the current technology has offered us to manipulate and control individual quantum systems, be it atoms, photons, or anything else, or some mesoscopic systems like superconducting qubits, it has opened up a huge opportunity to do 2 things simultaneously. So I think it's a very good opportunity. You always have an answer if you're working on some such thing, as to what would be its application, at least in the context of various things that these quantum technologies are projecting to offer. That was the thing which I wanted to say.
Professor Haroche, if you may sum up.
To sum up is difficult because a lot of things have been said, and I think what I find very positive is that we all agree about the spirit of what science is and what science should be and what the connection between basic and applied science should be. So let me first start about talking about the French-Indian cooperation, because we have here the people responsible for the Cefipra, and I think from my own experience that the most useful kind of cooperation is the one which comes from bottom up, from personal connection between scientists working in different countries. And I think we have to build up over things which have already happened. The fact that some Indian colleagues here have been trained in France in different laboratories should be a starting point to increase this kind of collaboration. Last Saturday, I was lucky to visit the Raman Institute in Bangalore, and I saw people, not only your group, but also the cold atom physics group, which was doing very interesting science, which is connected to what is being done in the LKB. And I think that one should try to increase this kind of collaboration by having exchange of students, exchange of postdoc, and having also colleagues coming to spend some time. I'm sure they will be very interested. Christophe Salomon or other equivalent people will be very pleased to come and to see what you are doing in this field. And in the field of photonics, it's the same. You have in France some startup, Candela, which is a startup working on single photon, trying to develop single photon sources for communication and for quantum computing. And I'm sure that an exchange between your group and there would be very fruitful and very interesting. Maybe organizing workshops where students would be invited from France to come here, or Indian students to go to France, would be a way to stimulate collaboration between the two countries. There is one characteristics in the way this kind of research is developing in France is the fact that several startup companies, some of which are very successful, are now existing in France. And maybe one should try to induce some kind of connection between these startups and the academic world in India. The startups are useful because, of course, they can attract money from outside the academic system, and there is a lot of venture capital for good or bad reason come into this field, and we have to try to take advantage of the good reasons, which is to develop research and to develop research at the intersection, at the connection boundary between basic and applied science. So I'm sure that that going in that direction, trying to develop the connection between some of these startup companies and Indian researchers would be interesting. These companies have been started by colleagues in the academic world, even if they have taken some distance with the industrial part of the activity. So maybe that would be good also to develop. And of course, it's for India, it should not be limited to France. In the European Union, we have a big flagship in quantum information, and maybe there are ways in which India could be connected to this research at the European level. So I don't see anything else to say, but I think it's a very promising field, since you want, and my colleagues have said a lot about what we can expect from the field in the future, as far as we can make predictions about the future, which is hard. And I always like to remind ourselves of the limitation of this game. When you ask this, the same kind of question was asked to scientists 100 years ago, and nobody was able to predict all what has happened since. The first, what is quote-unquote first quantum revolution, which is the laser, the MRI, the atomic clocks, the GPS, and so on. nobody had predicted it. Even when even Einstein, Bohr, Heisenberg, Schrödinger were unable to predict what would happen. And this has happened. So we still have to go on and to hope that interesting application will come. In fact, we have also to realize that we have formidable challenges in front of us that we did not talk about, and like the climate change, the health issues, and so on. And to solve these issues, you need science and more science. And quantum technology are only a part of the solution will come only partly from quantum technology, of course, but one should develop science in general, not only quantum science, for this to be successful. And again, this comes back again to education, to improvement of education and science education in general.
Thank you very much. I would like to thank all the panelists for a very stimulating discussion. I'm sorry we exceeded the time a bit. So we have time for a few questions from our young audience here. So please raise your hand and feel free to ask.
Hello, can you hear me? Hello, this is Vinita Sharath, not so young, but yeah, very curious and very young. If you see, my mental age is like a child. So I am presently working as a science and STEM head at Shiv Nadar school. So there are 4 or 5 branches, and through Miss Vinnie Mathur, we had been constantly coming to this organization and having all these lectures and facility at Shiv Nadar University. So my question is, there are 2 questions. One is to the eminent scientist who is, I think, sorry if I pronounce wrong, Dr. Rapol. You know, whatever you were saying, I can very well understand that the high school students was easily understanding the field what you were talking. And so was to some extent with Dr. Urvasi when she talked about single photon, and then the TIFR scientists. So my question is, when it comes to trap young mind, and I quote here what Dr. Serge said just now, way to attract bright minds to give these challenges to students based on the basic sciences. Now, when I look to these community who are sitting right in front of me, is there something where you are providing a kind of internship or workshop for high school students? So I was trying this since long, and this is my 30 years of teaching physics in high school, and I had been continuously sending students to CERN, and every year children go to CERN and ITER. But when I look at our own, in India, I'm not getting a platform where the students can do a kind of workshop or internship. I've seen with time that many of my students are scientists at Max Planck Institute, at Harvard, and those had been exposed to all this organization. I'm very thankful to CERN and ITER who had given this platform to us. So it's a kind request. If it is yes, how can we approach this? And if it is no, please consider us. Thank you.
Let me take this question. So
yeah.
I'll talk about what's going on at my institute at ISER Pune. So there is a science activity and outreach center which regularly organizes visits by school students and high school students for doing various science activities. So there is a workshop, in the sense there is a laboratory for playing with all kinds of small toys through which they learn basic concepts in physics, for instance. So those kind of workshops are regularly held. In addition, there are also workshops for teachers themselves to how to train the students using these toy models and things like that. Although, I mean, I must say that I am not involved in this activity, but my colleagues, some of my colleagues are very passionate about this, and there is a very active program at our institute. I'm sure most institutes have.
Yeah, so I'll add to that, Umakant. Yeah. Can you hear me? Can you hear me? Yeah. So we actually at RRI also have a very strong outreach group. And in fact, National Science Day is coming up. That is one day in which the institute is opened, that is one specific day in which it happens every year, where we have these school students and college students, they come and they visit. We have different experiments that we show them, then they visit the museum, and so it's a whole day event. That is one day for sure, but then it's actually is happening now with our new director coming in. It's happening almost every month. So we, some of us, sometimes we know who they are, sometimes some of us don't even know, because we have a very dedicated team and they approach people according to the students they are inviting. In fact, me and my postdoc and students, we have actually built a demo of the Raman effect coming from Raman Research Institute. So this is something that we are now encouraged a lot to do, to come up with small demo units to demonstrate phenomena which otherwise they just hear about, right? But then having said that, we also have what is called the World Quantum Day, which is coming up on 14th of February. And I'm representing India in that forum. So last year we had organized a Quantum for School event. In fact, Vijay was one of the speakers there and so on. And unfortunately, last year was still a bit of a COVID thing, so it was online. But it was also a little fortunate, not the COVID part, but the fact that we could actually reach out to students from all over the country. So we really had lots of registrations from students from different schools outside Bangalore as well. So Quantum for School was organized, and we had many lectures in that. So we are doing the best we can as a research institute to open up our own labs, to come up with models, as well as organize events at institutional and global level. Yeah. You want to add something?
I think maybe to specifically answer your question, it's possible that we don't have the equivalent of a program like maybe what CERN does. But TIFR also has a fairly active outreach thing, and we have a foundation of Science Day happens in November, and then also the Science Day in February, National Science Day in February, where we have open house. But it's not open to the general public in the sense that we just don't open the doors of the institute because of the logistics involved. Our team selects about, 30 to 60 schools, I think from students in class 9th and 10th or 8th and 9th, I'm forgetting now. And I think what typically happens for these kind of programs is that you tend to focus on less privileged schools, people who might not even know whom to reach out to. But I'm sure I have seen visits from schools which have put in a request. So, if you just reach out to our public relations office, I'm sure they will encourage or try to organize an event. But of course, being a huge country and one cannot accept all of these requests. I'm not involved in that part. But yeah, it's true that we don't have special internship programs for the school level where we bring a large group and let them stay for an extended period. It's usually one day kind of event. At least that's what they have been focusing on. Our team actually also goes out to small villages and does science demos and excites them about career in science as well. But mostly it's restricted to our geography in the state of Maharashtra, at least for now.
Okay, thank you. We'll probably have time for one more question. So
maybe from a student.
Yeah, maybe from a student.
There's a student here.
Yeah, please. Yeah, please.
Am I audible?
Yeah.
Hello, I am audible to you. First of all, good afternoon to everybody, and I would like to thank the organizing member and the college for such a great lecture, and especially to Professor Serge Haroche and other members. I have 3 questions. First of all, I will ask first of my question.
Please keep
2
it
questions
brief.
are important.
Just one question, please, per person.
Yeah, I will ask the most important question.
Okay.
As I am an undergrad of only in 3rd year right now, I have a question. If you have any idea, first of all, how to check it and stick to it. As I am a child, I have a lot of ideas regarding physics and our universe, and how to check it and stick on it.
How to check?
How to check it, whether it is correct or wrong, or stick on it and work on it. If you have any particular idea about anything. Yeah? Sir, Serge Haroche, please.
Yes, in fact, you are defining what research is about. You have to have an idea, and to stick on it, it depends whether your ideas correspond to observations or not. But the science has always been a kind of dialogue between observing things and building theories, ideas around this thing, and checking whether your ideas are correct or not by trying to use these ideas to predict new phenomena, whether you observe them or not. If you don't observe them, it means that your idea is not good and you have to change your idea. So, in fact, I think what you are, the idea you are addressing is the basic idea of science in general, which is a discussion between the observing the world outside and building theories and trying to find out whether the theories are right or not by confronting the theories with observations in a rational way. And we are living at a time where this becomes sometimes problematic. Instead of observations, you have a lot of fake news going around, fake observations, and instead of theories, you have opinions, and you have to distinguish an opinion from a theory. An opinion is something that you can just declare without having to prove it or without having to confront it with observations. A theory, an idea, a scientific idea is something that you have to confront all the time with observation in a critical way. And that's what science is about.
So one last question from a very young friend.
Hi, professors. It was very enjoyable listening to your speeches and knowing more about your work fields. Sir, so we know how particles get entangled. We have witnessed particles getting entangled. But the only question that boggles me is, why do they get entangled? No, sorry, not why do they get entangled. Why do they get entangled? Why do they mimic each other while getting entangled? What's the explanation behind it? So, can one of you please explain?
You have a specialist of entanglement here. Entanglement is a phenomenon which is directly related to the superposition principle of quantum physics. The fact that, quantum physics has started when when scientists like Einstein and de Broglie and Bose have understood that matter has a wave property. What does it mean? If a particle has a wave property, it means that the particle, before you measure it, can be everywhere in space. And this is what the superposition principle says. Before you make a measurement, a particle is quote unquote at the same time in different places. And only when you measure, you force the particle to be found at a given space. So this is what the measurement does. It means that the measurement is perturbing the system in a way which would force the particle to be found here or there. By the way, this means that the quantum physics is non-deterministic. When you do an experiment, if you do it over and over again, you will find different positions because the wave aspect means that you have a probability wave to find the particle at different places. Once you have admitted that, if you have two particles which have interacted with each other, if you measure one, it will have immediately an effect on the other one. And this is what entanglement is about. Entanglement means that when two particles have interacted in the past, they are now part of the same quantum system. You cannot separate their behavior from one another. And this is what entanglement shows. But this is very strange because it's introduced a notion of non-locality in physics. What happens in one part of the universe is correlated to what happens in other parts in a way which cannot be explained classically. But it does not mean that you can communicate faster than light. So it's not contradictory with the theory of relativity. And this is what makes the subtleness of all this. Quantum physics is consistent with relativity, and we have a world view of the universe in which you don't have any contradiction. You have strange things, you have non-intuitive things, but they are not contradictory with the basic laws of physics.
Thank you so much. So before concluding this session, I would just like to mention that SNIOE has always has a very strong French connection, and also particularly in this research area because of none other than our previous Vice Chancellor, Professor Rupamanjari Ghosh, who is right here in the audience. And she has run several very successful Cefipra projects in the past. Not only that, faculty members in chemistry as well as in biology have had French collaborations through Cefipra, even though they may not have been here at that point of time. I myself was a postdoc at some point in a Cefipra project. So I would also like to mention that it was a great moment of pride for us when Professor Ella Aspect, who was conferred upon with an honorary doctorate by SNIOE during its 2021 convocation, was awarded the Nobel Prize in Physics last year. We hope that the ties between SNIOE and India in general flourishes even further in the near future via lots of fruitful collaborations. So let's end on that note.
Thank you.
Yeah.
Just want to, of course, thank Shubhro. Yeah. I mean, on behalf of, I think, all the panelists here, I don't think, I think you took your fear on exceptionally well. You should go into the army. I think it was a wonderfully conducted session. I don't know how useful the session was, but he did a fantastic job. So a round of applause for him.
Thank you. Thank you very much. So
I think all of you were fantastic. Thank you so much for being here. And it was a very invigorating panel discussion. And I'm sure there are a lot of takeaways for our young students. I would now like to invite upon stage our Vice Chancellor, Dr. Ananya Mukherjee, to give the vote of thanks. Thank you.
So where do I begin? It is, of course, my privilege to have the opportunity to offer a vote of thanks, although I do not really have the words to express the gratitude and the excitement that I feel today. Professor Haroche, thank you so much for including us in your visit to India and for making quantum sound so simple. From the very moment we announced your visit until now, I am inundated by messages from different people for excitement and gratitude, and I'm sure we are going to receive many more. I'm particularly grateful for the support of basic science in which you spoke, and that basic science cannot be just borrowed, that universities and academic institutions need to have a commitment to the development of basic science, and of course acknowledging the virtuous cycle between basic science and technology. It is not easy for institutions to do so, but I would like to say that this institution believes in the importance of basic research. And Dr. Sengupta, you thanked Dr. Ghosh. You stole all the lines that I wanted to have about her and about about Alan Aspect, but thank you for doing so. And thank you, Dr. Ghosh, for starting this university on a path of research. And I don't know if we'll have time to visit the R Block, which is something that we are very proud of. To the panelists, we will surely be calling on you for more. I've been getting messages from people that they want to hear more about what is going on in India, about quantum, with the hope of building a collaboration around the endless frontiers of quantum. And we are deeply grateful to you for joining us today. Attaché Robasson and the Embassy of France, thank you for making this happen. As you heard, many of us are keenly interested in collaborations beyond borders and beyond disciplines. And we do hope that this marks a beginning in those directions, that this is not just one more of those discussions that happen which generates a lot of appetite and then not much comes out of that. Dr. Seth, Director of Cefipra, thank you so much for the opportunity and for the ease with which you made it happen. I think I've met you only once before at the tail end of another event on a very windy evening for one cup of tea. And there I expressed the interest that we would love to host some of the guests you bring. And then less than 60 days later, here we are. So it was we are very grateful for this opportunity. And I also want to thank our team at the university, beginning from our senior leadership, our faculty and our students, and our execution team who worked arduously for this event. And finally, a word for all the students from the various schools and universities who are here today. As you heard, the message to you is to be bold and to be unstoppable in your quest for knowledge. As Professor Haroche told us through his own experiences and through his message to us, that there is no shortcut to science, and it is not only important to learn science, but it is much more important, if not equally important, to foster a scientific mind, to keep alive curiosity, and to be bold with that curiosity. So as I said, this university very much believes in those values, and we hope to work with all of you to take forward that scientific temperament and the worldview of science and collaboration as we heard it being articulated today. Thank you.
Thank you, Dr. Mukherjee. May I now request Dr. Galande and Dr. Mukherjee to kindly join the panel for a group photograph, please. Thank you. Once again, thank you everyone for joining us this morning. It was a real pleasure having you all over. I request the panelists to now proceed to the faculty lounge for lunch. And I request everyone else to please remain seated until the guests leave. Thank you. For the school children, we have a little campus tour planned for you. Our interns will take you around. And everyone else can collect their refreshment boxes from the ground floor after the event gets over. Thank you.